In this video, I will share an experiment to determine forbidden energy gap of a semiconductor material. Energy level diagram of an atom represents energy levels of electrons belonging to different orbits inside the atom. When atoms form a material by chemical bonding, energy levels of electrons inside all the atoms get slightly changed due to interaction between electrons and nuclei of various atoms. The closely spaced energy levels of electrons form energy bands. Energy band of electrons belonging to first orbit of all the atoms is called first energy band. Similarly, energy band of electrons belonging to second orbit of all the atoms is called second energy band, and so on. Energy band of electrons belonging to valence orbits of atoms is called valence band, and it has bound electrons which take part in chemical bonding. The valence band electrons which have no role in chemical bonding are called free electrons, and the energy levels of these free electrons are higher than the energy levels of bound electrons. The energy band of these free electrons in a material is called conduction band of the material, because conduction of electric current in a material takes place due to movement of these free electrons. Energy gap between highest energy level in valence band and lowest energy level in conduction band is called forbidden energy gap. No energy level of electrons is allowed within this forbidden energy gap. Forbidden energy gap is about 1 electron volt in case of semiconductor materials and is almost zero in case of good conductor materials. The value of forbidden energy gap is very large in case of poor conductor materials. In case of semiconductor materials, forbidden energy gap is related to electrical conductance sigma, as log sigma is equal to minus Eg divided by 4.606 K into 1 by T plus log of some constant C, where sigma represents conductance as the ratio of current to voltage. T is absolute temperature of the material. K is Boltzmann constant. This equation shows that if log sigma is plotted against 1 over T, a straight line graph will be obtained, and graph will have a negative slope of magnitude Eg upon 4.606 multiplied with Boltzmann constant K. From the slope of graph, energy gap can be determined using the value of Boltzmann constant in SI units. Energy band gap can be obtained in joule, and then by dividing with 1.6 into 10 raised to the power minus 19, that is charge on 1 electron, the value of energy band gap can be converted into electron volts. In this circuit diagram, reverse bias semiconductor diode is held in an oven keeping the applied voltage constant. Reverse saturation current passing through the diode is noted at different temperatures. Let me introduce the apparatus to be used in this experiment. This is semiconductor diode. This is ammeter for measurement of current. This is voltmeter for measurement of voltage across diode. This portion is DC power supply. This is oven. Now let us make various connections in accordance with this circuit diagram. Connect negative of battery to negative of ammeter. Positive of ammeter goes to P side of diode. N side of diode is to be connected to positive of battery. Connect positive of voltmeter to positive of battery and negative of voltmeter to negative of battery. Switch on power supply. Oven can be switched on with the help of this knob. Observe the rise in temperature of oven as indicated by thermometer. With the help of this knob, adjust the voltage across diode so that ammeter shows sufficient reading. Keep the switch of oven on until temperature rises up above 80 degrees Celsius. Now switch off the oven. Note down the current readings from ammeter against the falling temperature in the form of a table. Make some calculations and plot a straight line graph of log sigma versus 1 over t. By dropping perpendiculars on axes of the graph, calculate slope of the graph. Using the value of slope, calculate forbidden energy gap of semiconductor material. Thank you.